Hey everyone, welcome to another episode of the Common Lisp Study Group. I'm your host Ram Vedam with Atlanta Functional Programming. Today we're going to be discussing the cells library. Library I kind of introduced last week during our Ask Us Anything session, but I was digging a little bit more during the week. Found some documentation on trying to get a better understanding of the library, and I'm going to present some of that material to you today. Before we get started, a couple of announcements. As usual, Atlanta Functional Programming is a meetup that is trying to promote functional programming regardless of language, and we are looking for speakers, for folks who are interested in speaking and providing a topic that's related to functional programming, anything related to functional programming, whether it be in C#, Kotlin, OCaml, F#, C++, or what have you. Please feel free to ping me and reach out to me. I'm Bugram on the Functional Programming Slack channel, as well as the Lisp Discord server. And I will submit your talks and get the talk topics presented and scheduled accordingly. AFP is now slowly discussing doing in-person meetups again. We are still in the hunt for a venue. Stay tuned to meetup announcements when we get our first meetup back on the schedule. That's going to be in person. We'll go ahead and announce that in the meetup page. Also, tomorrow, just a reminder for folks who are going to be joining us for our Haskell study group, we will be covering the topic of recursion, which for folks who are following Learn You a Haskell, it's essentially, if I remember correctly, Chapter 6 is in Learn You a Haskell. It talks about recursion. Of course, if you're following us using the Haskell book that we've been using, Haskell Programming from First Principles as well, that is Chapter 7. That is, well, no, it is, I think it's something else. Let me just pull that up quickly to my notes. Pretty sure that is Chapter 8, actually, but I could be wrong on that, too. Ebooks. It is chapter book. It is Chapter 8. Sorry about that, not Chapter 7. Chapter 7 is what we covered last time in the Haskell programming book. So that's tomorrow. It's at 1:30 to 3 p.m. Eastern, 3:30 p.m. Eastern time. Please do your appropriate conversions to get the time zone that you're currently in. My apologies ahead of time for not putting in GMT, but we'll talk about that. Okay, so let's talk about cells, right? So what is cells? As I mentioned last time, cells is a library that allows you to do a sort of a data flow programming model inside of your program. It's very much the author of the library, Kenny Tilton, a very long-time Lisper, ended up taking cells and the ideas of cells and actually adopting it in other languages, particularly right now, most recently, he converted the cells engine inside Clojure, and he ported it over to Clojure and Clojure Script, so you can now use it. For folks who are interested in that, I encourage you to also check out the Matrix library. It's the equivalent of cells that we're going to be covering today. It's already available for you as an open source project that you could check out on GitHub. Additionally, cells itself, which was originally on I think it was on SourceForge or CVS or something like that a long time ago, over the years has been moved over to GitHub as well. I posted the GitHub link to the project in the YouTube description for folks who are following us on the YouTube stream. That will help you get started the on the library. And there is a wiki page there. Although some of the wiki examples in there, you're going to have to do some small adjustments based on what we're going to be covering here today. That's inside Common Lisp, particularly just because of the fact that, at least for those of you who kind of follow a very similar model that I do, in that you do not do a use package inside of your def package definition. It would be useful to know where certain symbols are special symbols inside cells, and how do you account for cases where you're using something that is not exported, and we'll cover that today as well. I think the most important thing to start out is with a brief review of the motivation. I talked about this last week, what cells actually does and what it's attempting to do. It is using the CLOS, the Common Lisp Object System infrastructure, to essentially create a model to allow you to write data flow driven programs. Now, a lot of folks who've dealt with data flow programming, okay, the first program that they may have come up with is spreadsheets, and that's what this has been. This library was inspired by. You got to remember the context of which this library was created. Cells is not a new library. Cells has been around since actually I was first introduced to Cells back in 2006, 2007, when I saw this small project that says, hey, we're trying to, this library allows you to write data-driven programs and allows you to hook things up in a very interactive way without you having to actually go and implement the observer pattern. So most people who are coming in from the object-oriented world, from specifically the similar object-oriented world, that is your C++, Java, and C# schools, you implement the observer pattern by creating an interface that will essentially register callbacks and then allows you, folks to observe a particular model, and whenever a change occurs, it will loop through all the callbacks that were registered, okay, that's observing on that model and causes some effects to occur. That's a brief, albeit contrived explanation of what the observer pattern is. I urge you guys who aren't familiar with it to go look up in your design pattern books to go and review it. But what Cells does is it basically takes this idea of observers and implicitly defines them inside meta classes that then in turn can hook up and make certain objects into essentially blocks that can throw out signals whenever changes occur. So this way you can go and register, if you will, a particular object if you know what values are ultimately changing, and basically based on that, behind the scenes events will get thrown in. All the objects will who need to recompute their properties can do so. All right. This the result of this is essentially a model and a library that allows you to maintain your data model consistently throughout the lifetime of the program. All right. Which honestly, for folks coming from the reactive world, this might become familiar to you because that's essentially the promises that reactive programming gave you, where you're no longer on demand pulling for information. Anytime a event is changed or an event occurs and gets pushed, whatever related interactions that are expecting that event to occur will update themselves accordingly, and you can guarantee, at least to some extent, that the system will maintain some level of consistency. Now, whether or not those, events are the ones that you want to monitor and act upon, that's entirely at the discretion of the system designer. But the ability to be able to just simply define declaratively what should happen when a particular events occur and what would happen, and put it as close to where it should occur is very, very useful from a maintenance standpoint, and from a systems understanding standpoint, because it could give folks who are looking at particular software systems a consistent model of what's going on. So Cells based itself on this idea of observers and spreadsheet programming, and that's where the name also came from, because a cell is basically kind of like a spreadsheet cell. And honestly, it was one of a class of libraries that were all being created around at the same time. If you're coming from, say, the .NET world, you may have heard of the iObservables and the RX extensions before ReactiveX came out, and RX Java came out subsequently. This was very much in the same kind of realm that Cells was also developing, although Cells has in my opinion, a much more consistent model of how to handle some of those changes. Additionally, if you're coming in from the Python world, you may have heard of a library called Trellis, which essentially is the same idea, that allows you to write reactive programs. So programs that change whenever their dependencies change. Okay, so that is models that have properties that change when external stimulus or external inputs, or even internal inputs that are being defined externally, change over time, to make sure that your data model and the state of your system is consistent. Some of the applications that are normally used in this realm to make things useful, where cells and cell-like libraries definitely apply in, are your standard graphical applications, where your graphical user interface is actually hooking up into, say, an external data source, and anytime new changes happen from that external data source that's being inputted into your system, the appropriate related components of your applications that are dependent upon those data items recognize the change and actually act accordingly. Some of this is related, especially in the case of GUI applications, where the user is interacting with the user interface, and you are having to act upon whenever a particular user interaction happens on a specific component, and that might trigger a series of events that need to be subsequently updated. Okay. To start with, I thought it would be useful for us to go with the basics example that I had found. It's a similar example that's inside the documentation, but this is just a very basic example of what you can do behind the scenes. Now, but this kind of gives us a sense of how to build a basic model of a cells program. Okay, all cells programs, and this is going to be a very cursory overview I'm going to mention, because there are a lot of other stuff around here that we need to cover before we get into things like, say, some of the more advanced features, right, around it. But I'm getting ahead of myself. So a cells program can be thought of just like any other class program, okay, that uses the Commonwealth object system, okay. But whereas you would be using a def class to define your simple object model, you would now be using a def model, which is defined inside the cells package, as you can see here. And this def model is a macro that itself converts itself into a def class behind the scenes. Okay, so this is what it kind of expands into. Okay, it's a fairly large class that goes through and defines a bunch of different functions related to instance initialization, some of the setter functions related for the accessors, and doing hooks into the actual cell model rendering engine. So it registers the class as being something that can normally be used not only as a normal cross class, so you can actually take the same cells model and hook it as a specializer in your def methods for other generic methods that are defined in your program. It can also be used to define more reactive ones that are actually registered as part of the cells library. Each def model, um, just like any def class, has a series of slots. Now, here's where things get a little different, okay? Behind the scenes, the slot is actually parsed and it is determined whether or not it's going to be a cell, okay, which, as you can see here, is indicated by this cell property. This cell property is actually part of the cell's keywords that are registered when you go and quick load uh, cells, all right? Um, if I haven't mentioned this ahead of time, I'm just going to mention it now. Cells is available on Quick Lisp, so you don't have to add cells into your local projects and then do a quick load, all right? There is some documentation out there that actually uses the old way of actually loading ASD files into your image. And I'm saying old way because it is still a valid way to load images into, in libraries into your system, but I would recommend you try to use Quick Lisp as a package manager and actually use the dependencies rather than trying to manually set all that up. You could certainly, maybe at some point when you're deploying, may use it for it, but even there, I would argue that Quick Lisp should be your go-to for adding dependencies for your common Lisp libraries. Now, by default, cells are actually set to true. So you don't necessarily have to define the cell as being true. I'm just pointing this out and using it for illustrative purposes. But there is one thing to note, that there are two other properties that cell can be associated with. One of them is if cell is specified to nil, okay? But it could be nil, true, or ephemeral. We'll go through each of these examples as we continue on our overview today, but I want to at least mention that by default, if you don't specify this property, your cell is going to be set to true as something as being an input. Okay, so you could certainly do something like this as to start things out. Right now, when you compile the cells, you may notice that that there's the init form is slightly weird here, and it's unconventional, and as well as the init form in the second property. Okay, cells that have slots, okay, that are input cells. Okay, these are cells that are essentially taking in some sort of user interaction, all right, or something that's being interacted with directly from, say, some external data source. These are labeled as C-in or C-input. Both are actually valid things to actually go and put in. But with C-input, you need to actually specify a couple of things being a list rather than an actual value. All right, as you can see here, C/input makes cells giving you not a proper list here. All right, we'll go through all the different types of ways of creating inputs here, but I'm just briefly going through some of the examples that I've at least covered. Okay. Once you have an input cell like this, you can now start writing what are called dependency rules. All right, you can actually create rules that are essentially it's a cell that explicitly calls out a observation that is going to change whenever a module, a input cell actually changes, or even other ruled cells that you are depending upon actually change. Okay. Um, these ruled cells has some sort of equation, usually normally associated with them, that behind the scenes will convert into an anonymous function that monitors the value, and it keeps track of specifically the prior value of the input cell that the equation is dependent upon. Okay, so let me explain that just a little bit so that it it gives some more clarity. Okay, on this, you have this input cell here, right? You want it to be used in some sort of ruled cell. Well, you specify an accessor, or in some cases, if you know that this is going to be an input cell that it's going to have a fixed value, you could certainly make this a reader. But really, if it's going to be a changeable cell, it is actually going to be an accessor. Um, then you specify this condition, okay, using colon C question mark. This is basically saying, hey, this is going to be an anonymous. This is going to be a rule that anytime cell one of the instance change, which is specified by you calling the accessor on the current cell instance, has encoded by cell colon self. Self is actually something that is not actually inside Common Lisp Object System because of the way generic functions are registered and automatically knowing what instance it's dealing with. But cells requires it so that you can actually take a cell instance and actually go and execute specifically on that cell instance, because its meta class hierarchy and its class hierarchy is slightly different than the one that's provided by standard def class. So using this self instance reference here, we can actually call the accessor on cell 1 and make this dependency, this implicit dependency, that if we read this is basically saying anytime cell 1 changes, go ahead and double it and set cell 2 to cell um, uh, to that value. Okay. One thing for most readers who are probably wondering, well, and we'll get to it. There is probably some questions related to, well, what are you talking about an accessor inside cell 2 there? What does that mean exactly? That actually is something that we'll touch base on in just a minute when we cover the ruled cells a little bit more. Given this simple model, we can go ahead and use our normal class make instance function to go and create an instance of this. Okay. This in turn now will give us the following simple cell instance, and we can actually go and use introspection to go look at the cells. One thing to note is when you introspect when you inspect the actual object in the inspector here, you may notice a couple of hidden variables. These are all associated with the underlying meta model that cells is built on. Right? As you can see here, it is maintaining a list of the children as part of the object instance, whether or not they've been flushed. The MD state is being awake is related to the whether you have an active cell object or an inactive cell object. This one, I'll be honest with you, I haven't dug into too deeply as to what exactly the implications are with MD state. That's only because one thing I will mention about cells is the documentation for simple models and even very basic usage is actually pretty well defined and actually works well. But some of the more advanced usage, I think, is still somewhat lacking for the Common Lisp port. It might be slightly different from Matrix. I have not yet gone and checked out that. But as I go through some of this and start exploring the library a little bit more, I'm hoping these discussions and this presentation of cells can be used as a form of a live documentation. And if things are changed inside the Common Lisp library, those are accounted for in upcoming episodes, so that you can go through and actually look at the life cycle and evolution of the library. Are there questions so far? Okay, feel free to ask questions and post them as I go through this presentation, and you can act. You could check accordingly, and we can talk about it. All right. So, given this thing, we now can illustrate what cells is all about. And to do this, I'm just going to write a simple function, right? And I'm just going to do this instead. I'm going to do some refactoring here. Okay, hello cells. Okay, so what we're gonna do is we're gonna create our basic example or handle, if you will, I'm gonna call it a model to instance the simple cell. And what we're going to do is we're just going to do times and maybe say 10. And what we're going to do is we're going to, do times and 10. Okay, and what we're going to do is we're going to simply format t cell 1. We're going to print out cell 1, and let's do this. Okay, and let's go ahead and print out cell 2 as well. And we're doing cell 1, we'll handle cell 2 of model. All right? Okay, so what I'm going to do now is the special sauce, if you will, right? What I'm going to do is I'm going to go into our model, and I'm going to change our input variable, right? This is the input cell that I was mentioning that is mediated and allows you to assign values at runtime, okay? The ruled cell, as you can see, is just going to compute itself. It's what's if you remember your data modeling classroom databases, think about this as being a computed property, not a property that's actually being determined by some user input. Okay, not something that's going to be inserted into. It's going to be the result of some other value that was changed externally. Okay, although in this case it's going to be internalized to the model. So here we're going to just go ahead and just change it to, let me actually change this to this, because that's a good counter variable. And anytime this changes, behind the scenes, if we actually, again, go back to this expansion, what's happening is we have these slot specs that are actually used to actually go and determine whenever a change occurs, to go and re-register and recompute the actual value inside cell 2. All right. This is the result of that question mark here, that conditional variable. This is the rule equation that behind the scenes gets converted into the following. It becomes an anonymous function that you can deal with, and it will trigger this anonymous function that's encoded in a C lambda that behind the scenes is all about retrieving the instance information from the cell's rendering engine to actually go and determine how to compute using that equation that you specified. Okay, so this is itself nothing more than lambda function. You can think of this as an anonymous function, and we're going to see cases where we're going to end up having to do this automatically, and use those maybe somewhat specifically. All right. So when we run this function here, and this is going to be the let me share my screen. One second. Sorry about that. So, um, so when we run this function here, let's go ahead and run hello cells. Again, it's going to loop 10 times, and then every time it does a set on the model, it's going to trigger the ruled cell to compute itself. It's going to call essentially that callback, and you're going to see the following. Oops, did I spell something? Yeah, I spelled something wrong here. My apologies. Let me try that again. Okay, let's try that again. So when you run this, you'll end up getting something like this. All right. Let me change this again so we can actually see the differences. All right. Okay. When you run it, you can see something like this. Anytime the left-hand side is updated, and the right-hand side, which is our cell 2, is automatically recomputed, and we end up being able to access that information. Now, a keen eye will be like, okay, this is all well and good. This is really nice. This is awesome. I can actually go in and change this, but I thought accessors means that you can actually do a set f on that instance, and you certainly can do so. And I can show this by creating an instance here of simple cell, and you'll see that we have our initial cell defined as 1 and our cell 2 defined as 2. But instead, let's try and change cell 2 to 3. Okay. Now, if we have cell 2, cell this, and cell 1 is now 1. So we have this inconsistency. So one thing that I would recommend is actually doing this instead. When you're using cells and you know what your cells are computed properties are, this might require me actually to restart my Lisp. So give me a second. Usually on the safe side, just to get rid of some of these uninterned symbols, restart my Lisp image. That's just the way I kind of work around it. Although you don't necessarily need to do that, you can always unintern it, and that's uninterning the set f expanders for these properties. If we go now into this, and we go and create now our cells. Our cell to make instance simple cell. We now have this, where you can now do this, cells, and we have our basic example. We have our, again, our simple cell. We'll notice that if we set cell 1 to 2, we'll be able to get cell 1 and cell 2 will get computed and we'll get 4, okay? One thing to note there is, though, now if we attempt to do cell 2 and try to set that, you're going to get an error. What? That's weird. That should not have happened. Let's see here. Did it actually change? Huh. I put that explicitly as a reader instead of a writer. Should not have a let's try this again. Okay. Weird. That should not. 1 second. Let's see something here. It might be that readers slightly read differently in the cells library than what our def class. They may have changed some of the semantics. So let's just go to simple class and do, a init form 0 accessor SA. Obviously I'm using very bad names for some stuff here, but it's just for the sake of example. So we now have this. Let's go ahead and do make instance, def parameter example make instance simple class. So now we have SA example, it's going to be that. SB is going to be 1. But if we try to do a set F on SB as example, and do 2, see, this is what I was expecting. The function of that thing is not defined. Which means that it is that cell. So this is the first lesson that we could see here. In cells, everything has an accessor. Everything, the cells themselves are going to be modifiable, which is a little disconcerting. But I'm just going to. We could go and look into this here. Forms, slots back in, get loot for things, instruction 9 are these setF expansions. Here it is. See right here. So even though we specified a reader only, not a reader and a writer, it still generated our generalized expander for cell 2, which makes it a modifiable model. So you have to be a little bit careful about some of these computable properties that this means when you're using the cells library to do your work. Personally, that's something that I think can be fixed. I think requires a little bit more macro generation. Like rules that need to be added, certainly it would require. It just needs to. Pull requests are welcome. So if we figure out some of these issues, and someone else sees clearly that they can be fixed, they can fix it. go ahead and submit your pull request. I think the author would appreciate the fixes coming in. But that's neither here nor there. You could still use this to do computable properties to actually go in and compute your models consistently using this library. Let's see, where is I? So let's get back to our cells. So we have this simple model here of a input cell, again, as defined by the documentation. These are cells that can be assigned new values at runtime, and they are the basis for how cells gets data externally. So you could think of this being used as essentially the gateway to actually trigger all the rules that you'll end up writing using the C question mark API. And there are many of these, by the way. There are actually different versions of this. I haven't actually encountered cases where I need to use any of the other ones, but just to show you, there are rules that, for example, if you want to do once only, if you want them to be specified for example, to take a certain number of arguments, if I remember correctly. I think it's this one that I played around too. Some of the untils, like n until, is run a number of times, I think, before some rules getting conditioned, and things like this. I'm not entirely sure where all of these are specifically used in what cases. I'm still encountering some of those, but I'm going to mention it anyway because of the fact that I'm sure there might be other folks that may have encountered some of this. And if you guys have some comments as to when some of these conditions, some of these rules need to be accounted for, please let me know, and I will go ahead and accordingly update this. Although I think I may have found some documentation that goes through some of these different rules. I'm still going through that accordingly. I will obviously mention that at the end, and we could certainly you can certainly use that as a reference for your future developments when encountering with cells. All right. One thing to note is having this cell model, okay, and these different cells. Each of these instances are actually registered by the cell system, okay, the rendering engine itself inside the running image. Okay, this is something to be aware of. Now, one thing to take note, okay, if you will. One thing to take note, if you will, is the fact that you can actually go in and reset your cell system by calling cells reset. Okay. This takes no arguments and it will reset the entire system. Now, what does that mean exactly? Well, we have this, these instances already available to you, right? Already changed. They're not. It doesn't mean that your instances are all going to be garbage collected and deleted and all this kind of stuff. What cells does is it provides a way to reset the event lists and the event streams that underlying it keeps track of, that it maintains all the interactions that might occur. All right. Sometimes, especially when you're interactively prototyping a particular system using cells, a particular error might, in a very rare situation, corrupt your system, and as a result, cells may not seem to work properly anymore. So this function allows you to go ahead and reset all those system calls before actually running new code that uses cells, and that's all that what that function does. It's good practice probably normally to when you're starting a new project or starting to do some stuff to just run cells reset. So in this case, what you would normally do in a workflow is you will restart your Lisp here. In this case, you run, you load your project. Okay, maybe you are in the project package to actually start interactively prototyping, and then you might end up deciding to first run a simulation. Before doing all that, you'd probably want to run cells reset. And then after that, you could probably run hello all your functions, and it'll be, probably the case that it will actually work as designed. All right. That's something to be aware of. I think in newer versions, like if you're like moving from other languages, some of this stuff may be done automatically for you. This is possible as well when you are again restarting your image and so forth, and that could accordingly be used to you know make sure that occasionally that the system is probably in a consistent state prior to actually starting new cells codes to act accordingly. All right. So this simple model is great, and you might have cases where this really will be helpful. But really, the power of cells comes from the fact that we can model conditions and rules slightly differently with a more complicated model. Okay. Um, there are so with a more complicated model, you need to start talking about well, what exactly are you end up you know the what exactly are you trying to model, and how often and when do you need certain conditions to occur? All right. Um, in one case, for example, it might be the situation that you have to write specifically types of rules that uh, that require certain semantics to be respected before in order especially when you are using those models to actually go and compute properties that are occurring probably at initialization time for some system initializations. Well, Cells has that covered for you because Cells has this third type of cell, which is kind of what I was alluding to in all these different kinds of rules. And those are your what they call lazy ruled cells. All right. So I'm going to expand this simple model, okay, with a simple lazy model. All right, to illustrate some of this. So in this model, we're going to still have a rule here. We're going to go ahead and instead of doing this, we're going to actually use once. Okay. There are actually three varieties of three other varieties of ruled cells other than the one that we saw where it triggers a change propagation event and update to that ruled cell anytime the model changes. Okay. The first one is something called once asked, which is what C $once is, if I'm not mistaken. This basically is something that you might use when you're like reading in configuration files and you need to compute certain settings once at the start of a program based on those configuration files, and then the rest of the lifetime of the program they're only going to be read by the rest of the application code. So you don't necessarily need to actually explicitly provide those values inside the config file. You can just compute them on the fly based on the inputs of the other config values that they are based on. In this situation, let's call this simple lazy cell. And let's do this and compile it. So when this happens, when you're using once asked, it computes itself only once, read all the time, and the only time it will ever change is the computer property will ever change is if you go and reinstantiate the class. So to show this, we're going to go ahead and make an instance here. Def class, sorry, not def class, my prior. Def parameter, simple lazy cell. Actually, let's just call this lazy cell. Make instance of simple lazy cell. And what this does is it computes, already cell 1 of our lazy cell as 1, and cell 2 as our lazy cell as 2. And now if we go ahead and attempt to change, say, cell 1 lazy cell to 2, if my understanding is correct in the documentation, this is not going to actually change our cell 2. It actually will not trigger a change propagation event. So if we do this and say lazy cell, you see that it hasn't actually changed. Okay. This is, again, useful for folks who want to have a bunch of properties inside of a config file, want other properties dependent upon those config values to be available at instantiation time. This is one particular use case. You can think about other use cases that does this, you don't you could keep your configs very, very slim, and actually make sure that only the bare necessities are around there. All right. The second type of lazy ruled cell is you could think of essentially is an application of lazy evaluation inside the cells library. This is called the until asked lazy ruled cell. It only gets computed when the it only gets computed when you explicitly call the accessor on that particular value. So if you're, and you could think of this where when you have to write a rule that's particularly complicated, might be somewhat long running, but you don't know necessarily how often it's going to be used. All right. In those specific situations, you may want to end up adopting an until the asked version of this. Again, I'm going to go ahead and make a new example of this guy and post this guy later. In this here, we have, again, instead of once, we're going to call until, I think it is. Okay. And we can see that there's some issues here. Give me a second here. Warning, undefined value. Oh, what? Oh, my apologies. Let me just do something here. This, and then say until here. Let's see if I can do that there. Interesting. This expansion might be slightly different than what I thought it would be doing. So one, so self. Let me use Lisp just for a second here. Let me do a quick load of this guy. See if this is going to give me the same issue. No, it did not. Okay. Probably was an issue when I tried to adopt it. Okay. So, compilation, undefined value, 2 warning conditions. It is a warning undefined of cell self. So I'm wondering if this will cause the same issue. Let's see. Oh, lazy until cell being instance of simple lazy cell until. And we can see that the variable is unbound. Okay, got it. So, this until asked function that I might be using might be the wrong one that we're defining. Again, there are certain the API kind of changed just slightly when between the version that I last utilized. Don't know if until asked was added to this until later, but let me go and look at um, let's see here. Let's do this, and let's go to that, and let's go and take a look at this one. It's all about the basic conditions. Okay, let me just go and look at this one here. Come on. Let's see here. This one is. Okay, and let's do this one. Let's see here. This this old test. Okay, so looks like C and until should be doing what I think it should be doing, but it looks like there is a issue in how I'm leveraging it. I'm gonna make a note of this, and then we can roll back and actually touch base on that one uh, a little later, because that specific one seems to be one of the ones that is the troublemaker that I just encountered on yesterday, and I forgot to make a note of it. Um, but I'll mention it now that lazy ruled cells, especially with the until on asked, is your on demand ones. The the third type of variety of cells, if you think about it, is always, which is not evaluated or observed until and not reevaluated until dependency changes are read as well. So the only time your properties in your lazy ruled cells is ever modeled, it's going to be during a read of the cell, and it will accordingly um, uh, make sure that your function gets invoked, the properties get triggered, the slots are updated, and then you can actually go ahead and leverage the model accordingly. So there might be a small but insignificant time where you're computing your stuff whenever you're doing stuff on demand. You just need to be aware that's how the rendering engine works inside cells itself. Um, where is all right. Okay, so the next thing that we're going to be talking about is just specifically just the idea again, what's happening with the data flow piece of cells. Cells itself usually trigger a propagation, a change propagation event. That's kind of how I'm thinking of it. Whenever an input cell, that's those defined by C in. So I'm just going to make a note here to here, anything that's defined by this CIN, okay, the C dash in accessor, is an input cell that if you end up changing, it will trigger a change propagation event. Okay, now that change event is going to cause anything that is provided by a rule to being computed as well. All right. One thing to note is rules can depend on other rules. Okay. So if we create another example of here with, say, we'll call it simple cell 2 for the lack of a better name. And here we just go ahead and say, well, I want you to double the first cell, the first value that cell 1 comes from. And then we might add another cell here that itself is dependent upon cell 2, okay? And cell 2 is going to be cells itself. Just let's go ahead and do exponent, okay? Everyone remembers exponents here. Yeah, that's right. Okay. And our exponent is just going to go with cube it. So what we're doing is we're first doubling it, and then we're going to cube it in the third cell. Okay, this obviously is going to have an accessor cell 3. Okay, when we create this model here, and what I'm trying to show and illustrate is that your complexity, your rules can depend upon other rules, and it'll just the chain that actually triggers it all is still the actual setting of cell 1. All right, the change propagation event is only going to change cell 1. Now, that being said, remember the limitation that I encountered earlier for folks who are just joining us and stuff. There is a reminder on this cell model that I'm just going to mention here, and that is the cell depth model macro creates a generalized expander for every property inside of the depth model, and as a result, and this is something to be aware of so you don't have inconsistencies here. If we, in this case, have cells that depend on other cells using conditions and serialize change propagation, although it could be done differently with different classes that are dependent upon each other. Here, if we go in and change this guy and do this, this is all well and good in the perfect case, as we could see here, but we could also make things inconsistent because we have this generalized expander that generated for us a set F expander that shouldn't be there, because we, in this case, if you can clearly see here, we said that we want this to be a read-only property. It will compute on the fly, but if we don't want it to be set behind the scenes. Well, from a user interfacing standpoint. And that can cause issues because, as you can see here, we'll get 8 here, but our cell 1 value is set to 3. Okay, and for folks reading the code, watching this, you can totally see that this could potentially cause some issues, some inconsistencies in your data model if you're able to just blindly set F some of these functions accordingly. Okay. One thing to note about cells is cells keeps track of not only the input cells that are being provided by a particular instance and so forth, so it could keep track of the propagation that's occurring. It also has an observer API as well. I mean, although I alluded to earlier that there are implicit observers, sometimes you might want to have an explicit observer function to do things like, say, side effects to cause other propagations to occur by making other models update themselves accordingly. I'm not going to touch base on observers today, just because I didn't get a chance to really dig into that particular API. But I wanted to briefly mention it to folks in case you guys are looking at this and wondering what these are all about. Okay. One final thing I want to mention and will show is a piece of the cells API that I just recently started to understand a little bit. Okay. I'm going to just briefly mention it here, and we can go dig into it probably in another episode. But that is, in cells, def model can take objects that are also themselves def model to be created into what they call a family. Okay, a family is model instances that can reference each other using a specific API that's available inside cells. Okay, and that is the FM API. You may have seen this earlier when we were encountering some stuff in the in exploring the drop down of the exported symbols. These FM symbols are all dealing with family of objects. Okay, that is model instances that can reference each other. Okay, um, we're going to go through one simple example of families here, but you could certainly probably can think about this. This is related to what we saw inside of our def models, specifically the if they are a family of objects, you're going to see a hidden value here called .kids that will tell you that there are some children that's associated with this particular main object. All right. Um, so one example of this is possibly us. I'm gonna give you the reference to this. Is there is a cells documentation that you could see that's available at this GitHub. Where are you? This GitHub address. That has some more examples of this, but I'm gonna this particular example I wanted to show and address, just talk through, just because it was a little bit it required just a little bit of understanding of the underlying cells API to actually get what it's trying to do. Let's say that you are trying to create, say, a family of nodes and operations with different calculations if you want to define like math operations. Okay. In this example, you may need to start first with creating a model of a node. Okay. Here, and what you have to do is when you're defining a model that's going to be a family, you need to have it inherit from family. Okay. This will hook and register this particular model up with the rest of the cell systems to recognize that it is a family, and those FM APIs that I showed you earlier become useful now. Obviously, here we could then specify some sort of input. Let's call this and say initialize to nil. Let's go ahead and then say that we have a initializer keyword value, so we can hook it into the rest of the actual system. And this is something particularly important because once you encounter this in your code, this should automatically trigger saying, okay, this is now a family of values that we're actually occurring with. Okay, when we compile this and actually see the expansion, you could see that nothing is really new in terms of the expansion for using a family, other than the fact that we have this now superclass on the family. Okay, so we haven't actually encountered anything special just yet, but now we can probably define, say, this function, let's say mathop family, that where we have in this a root, okay, that we can make an instance of our node with val, okay, being a ruled cell. Okay, the root of the tree is going to be a ruled cell that applies, let's say, summing up, okay, all the values that we collected the kids inside of the family node. Okay, how do we get the kids though? Well, there's a function inside um, uh, inside cells called kids. Okay, and you can grab it this way. Okay, you can actually get the kids. Now, you might be thinking, well, there's this other function called this kids. What is the difference? If you are dealing with just all the kids in the model, okay, you want to call this accessor, okay. That caret kids, if I'm not mistaken, and again, unfortunately, that caret API is fairly new from it looks like from recently it was probably added. That, as I understand it, is if you're dynamically adding or you're dynamically removing kids from your family of objects and your family system that you're trying to change, that will trigger an event. So caret kids is actually a pointer to the collection itself, not the individual. It's not returning the collection as part of the it's not actually giving you the values of that particular collection. So let me do this. And since each of these kids are themselves going to be nodes, we're going to have to first call the accessor on them. Okay, so we're calling val on them. Okay, so now we have this root node. Okay, but we need to now specify all the kids. Okay, let's make a couple of kids. Let me just make sure. This one? Nope. This one? Yeah, that's it. Okay, hold on 1 second. This one? Yeah, okay. Now we have to specify in here the kids, okay? Now the kids themselves could be just, a finite list in this example, but it could be other kids. You can totally see ways to actually add them dynamically or using another function statically accordingly. But the way you would want to first set this up is to call the function cells the kids. This function here if we describe it, is a macro itself that's essentially registering each of the kids inside the actual collection. All right, inside the actual root of the node instance. So the way you do this is now you can now create a make kid, which itself is a reference to make instance behind the scenes, and you specify. So think of make kid as nothing more than a reference to make instance. Okay, if it makes it simpler for folks. Now you're specifying, well, okay, what is the name of this kid's name of this kid that we have in our model, so we can keep track of it. You could totally just say ND name. And you can provide different names for this. We're going to use something simpler so that it's easier for folks following the documentation to actually go in and actually keep track of their objects. Let me just do something here. Keep track of this guy here. Okay. So let's see here now. Let's call this N5. And just like following the documentation, we have this. cin5, oops, let's do that, then cells make kid, another node that itself could have kids, okay? So we say value, going to be itself a condition, okay? And this guy is going to be a ruled cell that is going to apply, let's say, multiplication on top of its children. Cells, kids, cells, self. And its kids are going to be themselves going to be condition, okay? And that is going to be on the cells, the kids, okay? And that will have, two children. So when you make a ruled cell like this, you could totally suspect that the children itself could change every now and then, and we're going to see how this kind of works in a second. I'm just trying to explain as I go along, just so for folks coming in, folks following along here, you guys get a sense of how this hierarchy is actually being created, right? So 7. This is going to be a val because we have an instance, and then this is going to be cells, say, and 7. And oops, my apologies. I forgot that I should do this. Sorry, I should do that. Wrap this in parentheses. Okay. And then we have cells, kid, node, N7, sorry, N9, cells, Cn. Okay, so this is our basic model, all right? What this is doing, again, is defining a simple family of objects that we can now use in the following, function itself, okay? First, when this gets instantiated, remember how ruled cells work. Ruled cells by default will trigger a change propagation event to first create a consistent data flow model at the time of instantiation based on any init forms and any init args that themselves trigger other rules, right? So when we, you could think of the first value of this, okay, and we'll call this the initial value of the tree, okay? This is already computed to us when we go and do this dynamic read, okay? Remember how the dynamic read stuff works, okay? But now we can also do this. We could say, well, I want to set one of the children, say that N7 or N9 to something else, okay? How do we do that? First, we need to go and figure out a way to grab that node. Well, we have something called FM other, okay? FM other is going to essentially do a search inside the model based on the model name you specify. So in this case, we have this model name, and now we need to specify the route that is going to happen, okay? Since we're calling this outside of a particular depth model, we're calling this outside of a depth model, okay? We need to actually provide an explicit instance here. That's where starting is going to be changed. The default value for FM other is essentially cell self, so it's expecting that internally you'll be calling it, but you can also call it on a running instance, okay, that it can go and retrieve on, all right? once it has that, then you have the model that you essentially want to call, okay? And now you can go and set this value, because this is just going to be a console, to 10. Once you do that, you can then, it'll trigger, again, a change propagation event, and then you'll get another new value of the tree. And it's going to propagate it all the way up, because this 10 converts triggers the rule that we need to multiply 10 by 9, which will give us 90, and then we're going to go and try and add 5 to it, and we'll get 95. Okay, pretty simple. Let's see if this actually all goes to what we expect. There we go. Now we get this warning, and oh, apologies. Here, cells, go, and make it. 1 second. Warning. Let's see, something's happening here. This may not actually go. Undefined variable cell self. What is it complaining about? Let's see. Here. This warning here that it's getting is... Well, let's see if this all works and see if we're getting an error. We're going to get an error message here. It looks like it's going to complain about the cell self being not available. But we shall see. Okay. Math op family. Let's see this. And we get cell self is unbound. In what function am I getting a cell self being unbound? Here. Right here. But what is this one? Undefined variable cell self. Okay, so we created a new node, and we defined the parent. Parent is going to be the node that we just defined ourselves earlier. Okay, so there is something missing in this model that I did not account for. Let's see here. Very well could be the case that I have to use okay. So let's see here. We could So its problem is the node that I created is not recognizing that it is part of a family here. Hmm, interesting. So how did we go and fix that? This is going to be according to this. It's going to be let's see here. This is calling the kids on this. Let me see if I can get this to be. Let me see this again. Make instance. Okay. Oh, hold on. Sorry. This is what I want to do. Let me see what happens if I just do this. Name conflicts. Yeah, of course I have name conflicts. So let me do this. Restart. Error compiling source. GG. Line 30, 28. Okay. Oh, apologies. That's something that should not have happened. Okay. Let's try that again. Okay. Now let's go shift here. Let's see if this all changed. Still giving us the error about the undefined instances. Now that we did this, I can actually get rid of this here. Since I'm now using the package, I can actually use the actual things and some examples. I mean, you don't necessarily have to clean it up this way, but I'm just making things a little easier for folks. So we have this here, this here, okay, and of course this. Okay, so we have one warning about the cell self not being defined still based on that. This is particularly interesting because this is telling me that sometimes cell self is actually doing what it's supposed to do, sometimes it's not. That's particularly interesting. Let's see here. So this is the root of the family. We created the root. Recognizes the family as being there. Let's see. What happens when I do this? Self is still unbound. It's because this error is still not going away. What might be causing this issue? This is it might be that I need to do this still because of this is kind of weird. Let me check something out here. Let me take this guy out and see what happens if there's any other issues. And here, let me see, instead of cells, do MD value, self. Undefined variable still. Interesting. So it does not matter at all here if I go in and create this model. So it seems to be some debugging issue that I need to go and take care of regarding this, because what kids is supposed to be doing is it internalizes the instance, the actual parent instance that we're creating, and passing that through to the actual underlying initialized instance code to recognize that the self that this top level function is defining itself as, that is the self that's actually inside and referenced by all of its children. It's kind of weird that it's not recognizing that. So I'm going to have to go and debug this a little bit more in detail. Fortunately, it's going to take a little bit longer than I expected to actually go and determine that. One thing that I wanted to mention, just because, although I apologize that I haven't had a chance to actually go and give you a good piece here of the family system here, but I'm going to mention it anyway for folks who are probably debugging some of this stuff. Okay, so there's an odd function taking in no arguments. Okay, so there's a comment in our chat about cell self. I guess is the question. Is the question about cell self being not taking any arguments, or Cell self is actually as you can see here, a symbol that is actually instantiated at the time that function a particular instance is actually going to be created, and it keeps track of that instance, and it's used like the disk pointer in other languages. That's essentially what cell self is. It's a disk pointer if you're coming from other languages, so you know what the current instance is. You can actually go and set f it whenever you need it to have the current instance that you're binding on. So oh, wait a second. That's it. That wouldn't have solved or been a problem. That's an idiotic thing. I mean, we need it, but it doesn't need to be there. Variable self is undefined still. Let's go and check, see if there's anything here. Let's see here. What is causing this particular problem here? Let's see here. This is creating. This did not make any sense. Let's see here. Okay, so I have to go and restart my Lisp because I'm getting rid of it. Okay. Oops, sorry, folks. That again. I don't know why I don't. Let me actually do this. Comment this guy out. And start this again one more time. Didn't necessarily have to do that, but I'm just going to go ahead and start it anyway. and level shift level, and go back down to our example. Let me go and do some readjustments of this so that we know where we are. Okay, and ah, 1 second. That's the problem. Okay, now I know what the problem was. This is essentially 3 and here. This, that. We still have that issue here. And that, oops, sorry. 4 unbound variables still. Alright. Let's see something here. Since we have this defined, let's go and have C make node. See what happens. Node 670 makes instance. Okay. So let's see what happens if I do make node cells. Sorry, val cells. We can apply this in add car val of cells kids of itself. It should create a new node. That's what it did. Oops. Now, let's go ahead and add here an additional node. Just a simple example. Kids. Now, what cells the kids does is it actually flattens the list, but here we're only going to be creating a new, a single node here. Okay, make kid node in the name 5. I'm basically boiling it down to figure out where the source of the lack of the self is actually being created here. Cells 5. Okay, I didn't specify the self. I mean the parent, so this should be okay still. So this is going to be a list of 1 kid. And this should create something, and it didn't. Okay, so for the time being, let's do something a little simpler. Instead of using the kids, okay, control that. Okay, let's see if that works. Okay, that still causes some issues. So there seems to be an issue with me creating families of objects. I'm going to debug this a little bit more just to see what happens. I really don't think it's useful for the stream to become a live debugging session for the time being. So I realize that we've gone over time. So I'm going to end it here today. Cells itself is a really useful library. I apologize that I couldn't actually get this particular example working as I thought I would. I didn't expect this particular problem when I was encountering it yesterday. But then again, I didn't get a chance to really play around with this example too much. So we're going to continue our exploration of cells next time. I wanted to briefly mention to folks that we're going to go on a brief hiatus for a couple of weeks, and we'll be back in August. So until then, I wish you all a nice summer, and those of you who are in the United States, happy 4th of July. I will talk to you guys next time. See ya. Thank you.